In this lecture, we're going to talk about the temperature dependence of solubility of solids dissolving in liquids. And usually when we're talking about this, we're really thinking about solids dissolving in water, right? That's our most common case. So in general, most salts are going to increase their solubility in water as that temperature increases. And that's why when you make simple syrup, you apply heat and you see a lot more of the sugar dissolves in the water than when it was at room temperature or even in cold water. And I actually have this graph here as well that shows a lot of different solids. But continuing on the sugar example, I've pulled that out as well from a separate source. So let's look at what happens as you increase temperature and you try to dissolve sugar in water. So we'll say we have 100 grams of water. And at 0 degrees Celsius, we'll be able to dissolve 179.2 grams of sugar in that 100 grams of water. Now, 100 grams of water is not like a huge amount. It's 100 milliliters, which in my head, it feels like about like a cup worth, right? I didn't do that conversion though. So as you increase the temperature, like you bring it up to just room temperature, you'll be able to dissolve 203.9 grams of sugar instead. So we see an increase in the mass of our sugar that we're able to dissolve. Now, if you heat that to boiling, right? If you boil some water and add the sugar, like you're making simple syrup, you're going to actually be able to more than double that amount. And you're going to get to 487.2 grams of sugar. So applying heat really increases the amount of the solid that will dissolve in the water. Now, looking at this graph to the side, looking at the solute of different, or the solubility of different solutes that are ionic compounds, we can see that as our temperature increases here on our x-axis, the solubility, which is being measured in grams per 100 grams of water, or which is about 100 milliliters, depending on the temperature. As this temperature increases, in general, we see our solubility increase. And so, like, let's just take an example. Potassium chloride is just beautifully straight, and sodium chloride as well. So it linearly increases its solubility as you increase the temperature. Similarly, sodium chloride does the same, but to a lesser degree. But it's still increasing the amount that'll dissolve in the water as you increase the actual temperature. Now, some of these compounds have linear relationships. Some of them have more logarithmic relationships. Like look at our potassium nitrate right here. It increases pretty significantly with temperature, but not in that same linear relationship. Now, one that's really interesting to me is cesium sulfate right here. So what's happening here seems to be the opposite. As we increase our temperature, our solubility decreases, right? Well, what this really has to do with is the enthalpy of solvation, essentially, or solution. Most ionic compounds are going to be endothermic as they dissolve in water because they're breaking those really strong ion-ion interactions, and they're forming ion-dipole interactions, which are strong, but there is some net increase in potential energy, right? And so we're not going to have the same or we'll have less enthalpy of mixing than we would the solvation or the dissolving of the solid plus the dissolving or the separation of the water. And so in those endothermic processes, we would have our solid in equilibrium with our aqueous solution. And if it's endothermic, we have to input energy to see it actually dissolve. We could think of that heat that we have to input as a reactant, essentially, right? We need heat and our solid and our water together to be able to actually form our solution. And granted, that heat's just taken from the surroundings probably. And so it feels like it just gets a little cold. We don't have to put it on a burner. But because of that, as we increase that heat, that temperature, we're actually going to shift this towards our products. And we'll talk about this kind of analysis when we do Le Chatelier's principles. This is a little bit of a sneak peek to that. We'll spend more time with it. But that extra amount of heat kind of is like having extra reactants around, and it means it will have more products form. In the case where we have something that is exothermic, then it's going to release heat as it forms a solution. So our heat is like a product in a sense. And so as we increase that amount of heat, we're going to see more solids form because we're going to have all these reactants around as we increase the heat, if we think of it that way. And so we'll have less of our solid form into the dissolved aqueous solution. And so really, as we increase our heat on an exothermic process where we're dissolving something, so if we have an exothermic enthalpy of solution, as our temperature increases, the amount of heat in the system increases, we're going to see a decrease in the rate of our solid becoming a solution. So a rate of dissolving. And as that happens, we'll see that as temperature increases, our solubility decreases. This is not the common case though, right? This is the exception to the rule. In general, most salts are going to increase their solubility with an increase in temperature, because most of them are an endothermic process. So we take advantage of the temperature dependence of solubility quite a bit in the lab. And so one of the things that we do is a technique that we learned in our previous class. It's recrystallization. It's where we dissolve something at a higher temperature or even room temperature, a solid into a liquid that is impure. And then as we heat this up, we can get a lot of our compound, a lot of our solid to dissolve in our water. Then we can slowly lower the temperature. And as temperature decreases, solubility decreases with it. And that means as that solubility decreases, we're going to form solids. And if this happens slowly, these are going to be crystals. Crystal can happen, well, I guess it can happen quickly, but typically as the slow formation of a solid allows those atoms to optimize where they'll be relative to each other and create a very ordered crystal structure. So then once we do this, we can crystallize this slowly and we'll have crystallized a pure sample, right? Our impurities will probably stay dissolved in our water. They'll have a different solubility in water than the compound that we're trying to isolate as a solid. And so this is a really nice, simple way to purify something that can be a solid. It's really nice. And then you just have to filter off all that other stuff. And of course, you've decreased the solubility with temperature, but you haven't completely made something insoluble. So when you do this technique, you always lose some of your product that you're interested in, part of the compound you're interested in, because it stays dissolved in the liquid, which we usually call at that point the mother liquor, which is kind of a fun phrase. So we've done this in the lab before and we'll do it again, and it's a great technique.